In this video, we're covering the topics of unsupervised learning. This will be the final learning objective for this course. You'll learn about understanding and applying K-means, understanding and applying hierarchical clustering, principal component analysis, as well as correlation analysis. What topics do you need to study? Here's a list of all the prior exams and how often they have appeared. As you can see, principal component analysis has come up on nearly every single exam. K-means and hierarchical clustering have not appeared on any official exams. The K-means has appeared on the hospital readmissions project. A correlation analysis has come up in more of the recent exams. The practice exams, apartment applicants, and health costs both have some examples of hierarchical clustering. What is unsupervised learning? Well, up to this point, you've really been doing what's called supervised learning. This is where you have some known outcome. Imagine a teacher in a classroom where there's some lesson and students are learning that there's a correct answer to every question. Conversely, unsupervised learning is where there's no structure. Imagine a bunch of kids playing Legos in a classroom as opposed to having a formal lesson. The goal is just to construct interesting patterns and to establish relationships using data. You can also break these down into continuous and discrete. So you have supervised learning where there is a target, and unsupervised where there is not a target. You call a discrete supervised learning problem a classification, and a supervised continuous problem regression. You call unsupervised learning, which is discrete, clustering, and unsupervised learning, which is continuous, a dimensionality reduction. So for PA, the specific topics that you have are GLM, lasso, ridge, elastic net, decision tree, bag tree, booster tree, for supervised models. And then for unsupervised models, we have everything in this lesson: correlation, principal component, K-means, hierarchical clustering. You will also use what's called semi-supervised learning. This is where you will use the results for a supervised model based on cluster analysis or PCA. A common example is using clustering to derive features and then using those features in a model. Most of you are probably familiar with correlation. Specifically, we'll talk about Pearson's correlation. This is where two variables are said to be positively correlated when increasing one tends to increase the other, and negatively correlated when increasing one decreases the other. A correlation is unsupervised because it does not depend on the target variable. So this is using the formula y, but y here is not referring to the target, it's just a generic number. Correlation only really works for numeric variables. Technically, you can use correlation if you have binary variables that are coded as 0 and 1, although this is not a common practice on exam PA, so I would be surprised if you saw it. The most common form of correlation is Pearson's. There's also something called the Spearman rank correlation, but again, that's less likely to appear. There's no need to memorize this formula either. So here's some examples of what correlations look like. The upper left, it has obviously a strongest correlation of 1. So notice that it's just a straight line relationship. The upper right, correlation of 0.7. So you could imagine that there's a very strong relationship here. As one variable increases, the other one tends to increase. A negative correlation implies that as you increase one variable, you decrease the other, and a correlation that's about negative 0.1 or 0.1 means that there's really not much of an increase or a decrease. It's also possible that you could have nonlinear relationships, like if your points looked like this, your correlation would be weak. However, you would still have some relationship in the data. It's because correlation only measures a linear association. Correlation does not equal causation. This is a very common saying. You'll need to know the difference when you sit for the exam. You'll be given problems just like this. They'll show you a correlation and you'll have to decide whether it's causal or not. So in this example, I want you to pause the video right now and see if you can come up with a logical explanation for why these two things might be related. Drownings rise when ice cream sales rise. It may seem that increased ice cream sales cause more drowning. But what's a more likely explanation? Rising heat may cause more people to swim, as well as more people to buy ice cream. The US murder rate from 2006 to 2011 dropped at the same rate as Microsoft Internet Explorer usage. What's a logical reason for these two things to be related? Well, this one was somewhat of a trick. Maybe there is no relationship. Google Chrome was launched maybe in 2007, and the government at the same time might have increased funding to police departments in high crime cities. Executives who say please and thank you more often enjoy better share performance. What's a more logical explanation for this? Is it because executives who say thank you are getting performance increases? Or could there be a non-causal relationship? Perhaps people who take the extra effort to be polite also take the extra effort to do their job well. Here's an example from June 16. You're given these variables. The target variable was the days spent in the hospital, and then you have the number of medical procedures, number of prescriptions, and number of prior hospital visits. They give you this correlation matrix in R, and as you can see, this is just the output of the R code. You don't need to do anything fancy to generate this. What I like to do is to copy this into Microsoft Excel, and then you can use the text to columns option right up here. Then go to conditional formatting and select a color scale, and then you can put it into the document like this. And so the diagonal terms show a correlation of 1, of course, because each variable is correlated with itself. And then the blue terms are the positive correlations. So for instance, number of meds is correlated with days in the hospital. And this is a positive relationship. So as you spend more time in the hospital, you're given more prescriptions. Conversely, there's a negative relationship between the number of inpatient visits and the number of prior procedures. But this is a pretty weak relationship. It's only negative 0.1. So if you were writing this in a report, you could say something like, patients who spend longer in the hospital tend to require more dosage of their medications, and thus they have a higher number of medications. You could also say patients who spend longer in the hospital also tend to get diagnosed with more procedures, and hence they have a positive correlation. It's important to examine your data for multicollinearity before you run a GLM. This is because it represents a number of problems. It leads to model instability, extremely high or low coefficients, standard errors which are very large, and this is not a problem for tree-based models. That's because tree models select the variables automatically. So if you have a tree with two correlated variables, only one of them will be selected as a split based on the Gini or entropy. There are at least two ways that you can deal with this. The first is that you can, for any group of predictors, just remove all but one from the model. And the second is to pre-process the data using a dimensionality reduction technique like PCA. So this is what you look out for. If you fit your GLM and you notice that there are some coefficients which are NA, that means that you have singularities in your model matrix. This is the same as saying that it is rank deficient. It only occurs when you have multicollinearities. In this case, I have numprox 2 and also numprox. So these two are actually the same variable, and so it's causing this singularity. So I could solve this problem just by removing one of these variables. K-means clustering is our first clustering algorithm. K-means first assigns each point to a random cluster. So you had to specify the number of clusters that you wanted to use. So in this case, there's 1, 2, 3, 4 clusters. So you said K is equal to 4, and then you ran K-means. Then it randomly assigned these cluster centers. Then it recalculates the cluster centers based on the average distance for each point. So look at these pink points, for instance. There are some points over here on the left, but then there are others over here on the right. So if you were to just look at the x-axis, you really want to move the pink center to the average, to the mean. That's why it's called K-means. So that moves this pink center over here, and then you reclassify each of the points as being in the cluster which is closest to them. So for instance, if you go back a slide here, you can see that these points here are all closest to this center, and so they all get put into the pink group. Then the next step is to recompute the distances for all the centers. So like look at these points down here. Is this point closer to green or is this closer to red? Well, really it's closer to red, so we're going to turn it into red. And then we update the cluster centers, like this green cluster center moves up here because there were a lot of points up there, and so forth. And then you keep doing this until you reach a stopping criteria. This is where the cluster centers stop moving. Like right here. If you were to run this at an additional step, for instance, these red points would all stay in their own cluster, these green points would all stay in their cluster, and so forth. Now, how did we actually measure distance? In that example, we were using Euclidean distance. Do you remember the Pythagorean theorem? I hope so. This just says that if you have a right triangle with sides A, B, and C, then A squared plus B squared is equal to C squared. So this gives you the distance formula. So if you wanted to measure the distance between any point and its cluster center, you just look at the distance, the square root of x minus the cluster center x plus the y minus the center of y. So a common question is, why do you need to apply scaling to the variables? So on this example, you have x1 and x2, and they both range from 0 to 1. But what if they didn't? Well, let's think about the distance here. So let's imagine this point right here. So let's look at d1, which is the distance to the brown center, and then d2, which is the distance to the red center. So I assign this point to be red because d2 is less than d1, right? Because this point's closer to red, of course. Let's say that I multiplied x2 by 100, right? Or in other words, x2 was on the scale of 0 to 100, and x1 was on the scale of 0 to 1. Then suddenly this distance d2 gets multiplied by a factor of 100. And so what you have is 100 d2 versus d1, right? And if I have 100 d2, this is actually a really big number. And so this picture is kind of misleading, but what you'd have is that this point would be closer to the brown center. So this point would become classified as being brown, which of course it would not make any sense. So that's why you have to apply scaling to the variables. So there are two ways that you can measure the fit of clustering. And I say the word fit with quotation marks because this is an unsupervised problem. So we're really not fitting anything. But we can measure how well everything's grouped together. There are two ways to do this. You can look at the between cluster sum of squares, which is where you just sum up all the distances squared from one center to another, right? So if you have 1, 2, 3, 4 cluster centers, then between cluster sum of squares is the first distance squared plus the second distance squared plus the third distance squared plus the fourth distance squared. So it's just the sum of these 4 distances squared. Actually, there are 5 distances because there are 5 blue lines. Conversely, the within cluster sum of squares is the sum of all of the points to their cluster centers squared. So you have to add up all of these distances, like all the pink points to their cluster centers, all the red points to their cluster centers, etc., squared. So this is useful when you have to select k. In this example, we're going to use the elbow method. So imagine that you had a line here, you drew a line, and you noticed like there was some elbow here. So on the far right, let's say that you had k was equal to n. right, where n is the number of points, then every point would be in its own cluster. And so your between cluster sum of squares would be as high as possible, right? Because you'd have a lot of cluster centers, and so you'd have a lot of square terms. If k was equal to 1, then you just have a single point, and so you have between cluster sum of squares is equal to 0. And so what you want to do is choose some point along this curve where there's an elbow, like using a value between k is equal to 4 or k is equal to 5 or 6 would be very reasonable for this question. If instead they give you a graph like this that shows the within cluster sum of squares, you want to use the same elbow idea, except you'll notice that the relationship's backwards. So here, if you had k is equal to n, then your within cluster sum of squares would be 0, because each point would be in its own cluster. So again, I would choose a value here where the within cluster sum of squares is low, or where there's kind of an elbow right between, I would use k is equal to 3 right here. One parameter that you'll see is called the n starts parameter. That controls the number of times that you run the algorithm. Why in the world would you want to repeat the algorithm? Well, it turns out that it can be unstable. So look at these 6 pictures. These are actually the same data set. Just look at like one point, for instance. Like, look at these 2 points right here. These 2 points are in all of the graphs, but in the first 2, they're in this pink cluster, and then they're in this green cluster. See? So each time you ran k-means with k is equal to 3, because there are 3 groups. However, the cluster centers are slightly different, especially along the boundaries. Try to draw a boundary around each of these cluster centers, each of these clusters, and you'll notice that there's differences. That's because of the randomization in the random seed. When you initially specify the cluster centers, that can have a big impact. It's called being stuck at a local minimum of the within cluster sum of squares instead of the global minimum. That's just a fancy way of saying that the algorithm, it does not perform consistently every time that you run it. And so what you can do is use a bunch of different starting values and then use the average cluster centers for each one. So let's just say that for this yellow cluster, like the first cluster center is right here, and then it was right here, and then it was right here. And so when you ran n starts is equal to 3, then you say the cluster center is the average x value and the average y value for those 3 iterations. The second way of clustering points is called hierarchical clustering. Now, what's a hierarchy? A hierarchy is a way of comparing things. Why would you want to use hierarchical clustering? Why not just use k-means for everything? Well, k-means is certainly powerful, and it works in a variety of problems, and it's fast to converge. But the advantage of k-means is that it doesn't require you to pre-specify the number of clusters, and it creates an easy-to-understand graph called a dendrogram. Now, what is a dendrogram? Well, let's take a step back. Let's just look at the clustering problem here for a minute. So let's say that you had a target variable, and that was the color. But you didn't put that into your model. So this data here represents just x1 and x2. So y is unknown. The target y is unknown. We're just showing it in the graph here. So imagine that you're training a supervised learning model, right? And you're pretty sure that there's some information that's not being included. Well, if you use clustering, you could maybe find that information in an unsupervised manner. One way to do that is using hierarchical clustering. So this shows different ways of clustering the points. So in this graph, there were 42 observations, and in this dendrogram, there are 42 points along the bottom here. So each of these end nodes is a observation. Now to start, you would say that every point is in the same cluster. And what you can do is specify a cutoff value on the y-axis here. And when you cut off the dendrogram, you group these points into 2 clusters. If you adjust your cutoff value to be lower, then you can increase or decrease the number of clusters. So this dendrogram has 3 clusters right here. Of course, if you set your cutoff value to like down here, you'd have a lot more clusters. The dendrogram, so in this example, you could find these 3 groups without including the target variable color in your graph exactly. Just by looking at the dendrogram and saying, hey, it looks like they're kind of like, there are 3 trees right here, tree 1, tree 2, and tree 3. Let's look at this in more detail. Here's a smaller example. On the right, you see the scatter plot of the points, and on the left, the dendrogram. Let's look at point 9. Point 9 is closest to point 8, right? And if you look at the height here, here's the distance from 9 to 8 is right there. Compare that to a point which is further away, like 9 to 1. So the distance from 9 down to 1 here, if I go down on the y-axis, I can see that this horizontal distance here corresponds to this linear distance here. There's only one parameter that you'll need to adjust for hierarchical clustering, and that is the linkage type. This is the way that distances are measured between 2 clusters. Default is called complete linkage. This uses the furthest distance, or the distance between the 2 points which are furthest apart. The other type is called single linkage, which measures the distance between 2 clusters by finding the points which are nearest, which have the shortest distance. The final topic is principal component analysis. PCA is a dimensionality reduction technique. So it takes in the original variables, x's, and it translates them into new variables called principal components. Just like the clustering, it centers with mean 0 and it makes the variance equal to 1. So this is just taking a transformation, x minus mu over sigma. Now, why is it called a dimensionality reduction? Well, let's say that I had 2 variables here, x1 and 2, and I just drew a line through them. Then I looked at the projection of each of the points onto the line, right? And so instead of getting a point like x1, y1, I just get a coordinate on the line that just tells me how far forward or how far backward I want to go on the line. That's my new dimension. So I just went from 2 dimensions to 1 dimension. Or if you have 3 variables, you can imagine that you have like some plane here where you look at the projection of all of the points onto that plane. And so you go from 3 coordinates, x1, x2, x3, down to like u1 or u2. But as you'll see in this example, for PCA, you actually go from the original variables down to principal components. So you would go from these x1, x2, x3 down to PC1, PC2 coordinates. So here's an example from the US arrests data. And you can see this in the study guide chapter. So in this data, each row represents a single state in the US. So there are 50 states. And you have these categories for crime and population: murder, assault, urban population, and rape. And what you're interested in is seeing if there's a pattern. Maybe there's like some geographic pattern, right? States that are close together tend to have similar crime patterns. And so you run PCA and you observe these 2 principal components. So this tells you that PC1 is a linear combination of the variables. It takes 0.53 times murder plus 0.58 times assault plus 0.28 times urban pop plus 0.54 times rape variable. Well, a more useful way of understanding them might be to look at a graph. This is called the biplot. Biplot because it shows 2 PCs. So on the x-axis, you see the first principal component. On the y-axis, you see the second principal component. each of the observations is a state. So these vectors represent the loadings for each of the variables. So notice that as the first principal component increases here, murder and assault also tend to increase. But urban population increases, but it's at a slower rate. So these numeric values are called the loadings or the rotations. They're called rotations because if you look at the biplot, it's rotating the point and rotating the vector. So look at this example for murder. So as you increase the principal component, you increase the murder rate also tends to increase. And this is a positive loading. Consider instead the murder rate for PC2. This is a negative sign. So this says that as PC2 increases, the murder rate should decrease. So as PC2 increases, that's as you move up along the y-axis, the murder rate should decrease. Look at that. As you move up here, you're moving backwards along this direction here. One more example, let's look at urban pop, right? As you increase the second principal component, the urban population tends to increase. And again, you see that that's a positive value. And so you can really understand the biplot just by looking at these loadings. There's also a strong connection to correlation. So look on this correlation graph on the left and see that the strongest correlation is for assault and murder. And look at these two. These are closely related. So variables that have a high correlation tend to have the similar vectors on the biplot and also similar signs on the loadings. Conversely, vectors that are not very well correlated, like urban pop and murder, tend to have a lower correlation. See, this value is only 0.1. So why do you need to apply scaling to PCA? Well, let's look at the units. The murder rate is the occurrence per 1,000 people. The assault is also occurrence per 1,000, as well as rape crimes. But then the urban population is the percentage of population that lives in the urban area. So this is 0% to 100%. So if you just look at the variance of these numbers, these vectors, the variance of murder is about 19, assault is about 90, rape though is much higher, about 7,000. So if you just tried to run the principal component analysis without applying scaling, you get something like this on the right, where there's just an unequal distribution of the loadings because the variances of the variables are so much different. So on the left here, this is the graph after you apply scaling. And as you can see, this allows you to interpret the PCA much more easily because the loadings, because all of the variables are on the same scale. So how do you choose the number of principal components? Well, you could choose only one principal component, and that would explain about 60% of the variance. If you chose two principal components, that would add an additional about 30%. So you'd have about 60% plus 30%. So you'd be able to explain about 90% of the original variance in your matrix just from using the first two principal components. And then as you add in the additional principal components, it will add less and less information. Now note, if you have four variables, you are having at most four principal components. And if you'd use four principal components, you'll be explaining 100% of the variance because you'll just be using linear combinations of the original variables. Here's an example of PCA. Use observations from principal component analysis to generate a new feature. So in this case, you have some data. You have x1, x2, x3, and what you want to do is maybe replace some subset of these features with like a single principal component. Like maybe you replace x1 and 2 with principal component 1, for instance. So your assistant has provided code to run PCA on 3 variables. Run the code on these 3 variables. Interpret the output, including the loadings and on significant principal components. Generate one new feature based on your observations, which may also involve dropping some current variables. Your assistant has provided some notes on using PCA on factor variables in the R&B file. So this is what the output is. So you can see that there are 15 variables in this problem, and so there are 15 principal components. You'll see the standard deviation as well as the proportion of the variance explained and the cumulative proportion explained. So on your report, you could say something like, running PCA on these variables shows that 22% of the variation is explained by the first PC, and 35% is explained by using the first 2. You will also want to look at the rotations or the weights. So here are the 15 variables on the x-axis, and you will see that they are all somewhat related. There's a road conditions variable, there is a light variable, and a weather variable. And so what you want to do is reduce this dimension down from 15 to just a few principal components. What really is the question said, interpret the output, including the loadings, also called the rotations, and then generate one new feature. So with everything that you know about PCA, you want to explain as much of the information about the weather and light conditions as possible using only a few of the variables. So naturally, you want to use the first principal component because this explains most of the variation. So an example is you say, so if you wanted to just recreate the first principal component exactly, you would just create a new variable in your data that would be negative 0.51 times this variable road conditions dry plus 0.09 times road conditions ice, snow, slush plus 0.056 times roads conditions other, etc., etc., etc. And you do this for all of the variables. But that wouldn't reduce your dimension at all. Instead, you can just try to choose variables which tell a compelling story. Remember, this is in a communication exam, and so the goal is to create something that is easy to explain. An example is a rainy or clear variable. This is 0.51 times conditions dry, and then conditions wet, weather clear, or weather rain. So in your report, you can say something like, applying these weights creates a variable that is strongly positive for rain and wet conditions. Now you can see that it's positive because these 2 loadings are positive, and it's also negative for clear or dry conditions. It makes sense to pair each of these as they would typically appear together. For example, rain on the roads, rain on wet roads. So if you want to, try pausing the video and see if you could think of another variable that you could create based on this information. How about high or low visibility? This would look at light and dark. If the light is daylight, or if it's dark out but there are street lights, or if it's dark out and it's dark, and if it's clear weather. So you could say something like this: applying these weights creates a variable that is strongly positive for dark conditions and strongly negative for daylight. It makes sense to pair each of these as they would typically appear together. For example, clear weather leads to brighter daylight. Cloudy weather would lead to darker, less visible driving conditions.